In this video, we're going to cover section 10.6 on hydrogen nucleophiles. And so we're going to be using two hydrogen nucleophiles to carry out nucleophilic addition reactions on carbonyl-containing compounds. Now, one of the most common reducing agents is sodium borohydride with the molecular formula NaBH4. And it can be used to reduce aldehydes and ketones to alcohols. Now, the basic premise is that sodium borohydride functions as a source of hydride. It's a hydride delivering agent. And the solvent functions as the proton source. So sodium borohydride can be carried out in a variety of solvents. We don't need all three solvents. It's just to show you that you could choose any polar protic solvent, water, ethanol, methanol being the most common solvents of choice. And this is the structure of sodium borohydride. You can see it's the boron-centered species where boron is taken on an additional bond to hydrogen. Therefore, the formal charge on boron becomes -1. And so it's going to deliver one of those hydrogens as a hydride, H-, in the formation of a new bond to that carbonyl carbon. So here's the mechanism that we saw previously in the last video, where we have nucleophilic attack now from this BH bond. So it's a hydride that's forming a new bond with carbon. And as the electrons of this BH bond are forming, this carbon-oxygen bond is breaking. And the net result of that nucleophilic attack is the formation of our tetrahedral alkoxide intermediate. And again, in the presence of a polar protic solvent like water, we will undergo a proton transfer reaction, which will generate the alcohol and produce some hydroxide. But again, because the hydroxide is a weaker base than the oxide, this reaction will be favored. Now, another common reducing agent is lithium aluminum hydride, which is abbreviated LAH. And here's the structure of lithium aluminum hydride. Similar to borohydride, we have the aluminum center forming 4 bonds to hydrogens. And it's one of those aluminum hydride bonds that will act as the source of the hydride in this reaction. Now, lithium aluminum hydride is a much stronger reducing agent. So as a result, we can't dissolve lithium aluminum hydride in the presence of a polar protic solvent. If we were to do so, it would simply react with the solvent and not with our carbonyl-containing compound. So you'll notice that when we draw our reaction conditions and how we carry out this reaction is that we will introduce the lithium aluminum hydride in a first reaction, and it will generate the alkoxide intermediate. And only after we've given that reaction sufficient amount of time to carry out the transformation to that intermediate, it's only at that point that we would slowly add in our polar protic solvent. In this example, we're using water as that source of protons, and so we'd slowly add that not only to convert the alkoxide to the produced alcohol, but also to quench any remaining hydride present in our reaction mixture. Now, the mechanism, nucleophilic addition, is the same as what we saw for sodium borohydride, where lithium aluminum hydride functions as a delivery agent of the hydride ion. So that's the electrons in this aluminum hydrogen bond that are undergoing attack onto the carbon of the carbonyl, breaking the pi bond of the carbon double bond oxygen to give you the tetrahedral alkoxide intermediate. And then finally, we get a proton transfer from our polar protic solvent to give us our final alcohol. So the mechanism for both hydrogen nucleophiles, sodium borohydride, and lithium aluminum hydride are the same. It's just the source of the hydride that's different. Now, when we start from, let's say, an unsymmetrical ketone, if that's reduced using our hydride nucleophiles, what we will obtain is a pair of stereoisomers, specifically a pair of enantiomers. And that's because, as we mentioned previously, we can have nucleophilic attack, we can have the delivery of that hydride from either side of that particular structure. So as a result, we'll end up with a racemic mixture, that is a 50-50 mixture of the two configurations if a chirality center is formed in our product. Now both sodium borohydride and lithium aluminum hydride, they will reduce aldehydes and ketones. But they offer one significant advantage over catalytic hydrogenation that we observed previously, in that they can selectively reduce a carbonyl group even in the presence of a carbon-carbon double bond. And so you can see in this example, we have this cyclic enone where we both have a alkene as well as the carbonyl group of the ketone. So if we use our new hydrogen nucleophiles, our new hydride delivery agents, both sodium borohydride in the presence of a protopolar solvent or lithium aluminum hydride carried out in two separate steps will produce the subsequent alcohol, but it will remain unchanged at the alkenyl part of that molecule. Whereas if we were to carry out catalytic hydrogenation in the presence of a metal catalyst, we would observe both reduction at the carbonyl group as well as the alkene. So these new hydrogen nucleophiles are selective towards reduction of carbonyls, but are unreactive towards the alkene. So this selectivity in the reduction process can be helpful when carrying out particular target synthesis. Now, since lithium aluminum hydride is much more reactive than sodium borohydride, we often will say that lithium aluminum hydride is less selective. And so lithium aluminum hydride will react with carbonyl containing compounds such as carboxylic acids and esters as well, but sodium borohydride being less strong will not be able to carry out those same reduction reactions. So as you can see in this example, both carboxylic acids and esters can be reduced using excess lithium aluminum hydride to carry out the transformation, followed by a quench with a polar protic solvent like water. So let's look at the mechanism for these two reduction reactions. Now the overall mechanism basically involves the transfer of the hydride from lithium aluminum hydride twice. So we still have in many ways nucleophilic addition occurring, it's just that we observe that addition twice. And so the first step, similar to what we observed previously, is the transfer of the hydride from lithium aluminum hydride to the carbonyl carbon, forming the alkoxide intermediate. Now, following the formation of this particular intermediate, what we observe is the loss of a leaving group. And that occurs because this particular intermediate is very high in energy. It's not stable. And so what we end up with after those two steps is the formation of an aldehyde. And that aldehyde will quickly undergo reaction with additional lithium aluminum hydride in a nucleophilic addition manner. So we see nucleophilic attack, that is delivery of the hydride reagent to the carbonyl carbon, formation of the tetrahedral oxide intermediate, and then once we're fairly certain that we've converted all the original ester to the oxide intermediate, we'll then do a water quench where we will transfer a proton from water to the tetrahedral oxide intermediate to give us our final alcohol. So the only difference from the previous examples of nucleophilic addition is that we're generating this high energy intermediate where we have a fairly weak carbon-oxygen bond that can be broken to generate this methoxide as a leaving group. And so other than that, the nucleophilic attack steps are identical, and as we said, the final step is a proton transfer to form our stable alcohol. Now, for the reduction of carboxylic acids, the mechanism is a little bit more complex, and I don't expect you to be able to draw the curved arrows representing this particular reduction reaction, but I thought I would include it into our class notes and discuss it briefly just to show you that we do have a fairly reasonable mechanistic understanding of how this reduction proceeds. So overall, what we observe is the formation of the alcohol. The means in which that alcohol is produced is a little bit different from what we observed previously, at least to the aldehyde stage. You can see that because the carboxylic acid has an acidic proton, we're first going to see a reaction between the hydride and that proton to give us H2. It's then that carboxylate species that will interact with the aluminum trihydride to give us this intermediate, and through some rearrangement, we generate the aldehyde. Again, I'm not going to expect you to follow the specific details of how we get to the aldehyde stage. But once we produce the aldehyde, then the mechanism is very similar to what we observed previously, where we have nucleophilic attack onto the carbonyl carbon. We form our tetrahedral alkoxide intermediate, and then we have a proton transfer step. In this case, we're showing the hydronium ion as our source of protons to form our final alcohol. So if you have any questions about nucleophilic addition with respect to the use of hydrogen nucleophiles, not only to reduce aldehydes and ketones, but now we've seen that we can carry out the same reaction with lithium aluminum hydride for esters and carboxylic acids. So if you have any questions about that, by all means, send me an email. Thank you.